Hello everyone, welcome to Sunday afternoon physics lesson. Today we're going to work on work and kinetic energy. Hey, call me Betty. Oh yeah, Ben, how are you feeling today? You were sick all night. Oh geez, that's horrible, Ben. Feeling better now though? Let's see who's here. Hello, Ben, Grace, Ishmael Ali, Deborah, Hero, call me Betty, Exploring Ginger. So, let me turn the music on. I hate silence in my ears. I hate it, hate it, hate it. There we go. I feel better. So today we're going to work on what we call work. When we think of work, I think I'm going to work. Well, I have work to do. Oh, good, Ben. Very good. But in physics, work is a little bit different. Depends on what kind of job you have if you're doing work. Well, technically, you're always doing work. But it's a fine line, I guess. So let's talk about this work. Work. So you remember force, right? So work is applying a force in a direction. Well, it's very hard to make it exactly. Thank you, Ben. To make it exactly the right thing. It's very subtle differences. One little word and make the definition wrong. So, how about this? A force applied to something to an object to move it or to slow it down. I'm sure if I thought about this definition long enough, I'd come up with a reason why I don't like it. Yeah, dog still hasn't found what it's looking for. So the way we just have an equation form, physics is best to describe things with equations because those are 100% perfect. F with a dot sign D. Now this dot sign, you may remember from algebra, that you can do something like this, like 2.3 is 6, right? It's multiplication, but this is a big dot. Big dot means something different. This is a small dot is multiplication. And you don't really use that anymore for multiplying things. I never use it. If I'm going to multiply 2 times 3, I put 2 parentheses 3, like that. A big dot is called the dot product. It's a mathematical process. Hey, Iranian Pride. If you haven't checked out Iranian Pride's new video of his balcony in Cyprus, you ought to check it out. It'll make you jealous. Very nice balcony. Iranian Pride. I would sit out in that balcony non-stop. I wouldn't come inside ever. I'd sleep out there. He's looking for something in the dirt. He wants to eat, I guess. So the dot product is a way to multiply two vectors, because this is a vector and displacement is a vector and work is not. So remember, this is force, this is displacement, and they're vectors. So you multiply two vectors and end up with a scalar. So a method to multiply two vectors and get a scalar as a result. So in other words, work is a scalar. That means there's no direction associated with work. Force is a vector, displacement's a vector. So there's a magnitude and a direction for force and displacement. So how do we do this dot product? Well, it's not that hard. There's two ways actually. F dot D. You can do it like this. F sub x times D sub x plus F sub y times D sub y plus F sub z times D sub z. Now what are these x, y's, and z's? So these are your three dimensions, right? X, y, and z. 3 dimensions. That's the first way. The second way is used more often because a lot of times you're not given the x, y, and d coordinates like this. So the next method is just f, the magnitude of f. See Ishmael? The magnitude of d times the cosine of the angle between them. So this angle between them, theta, this is called theta. Remember theta? Just an angle. It's the angle between F and D. So far, that's a good place to take a break. Any issues with this? Anyone have any questions about what any of this means at this point? Before we do an example. Okay. So let's see here. We have a flat surface, we have a mass, and we have a rope. Hey, Katarina. You have a rope applying a force this way. It's moving this mass a distance, let's say d. So F moves M a distance d. How much work did F do? Oop. How much work did F do on M? Well, work is magnitude of the force, magnitude of the displacement, times the cosine of the angle between them. So the force is just F, displacement is just D, times the cosine of the angle. So what's the angle between F and D? Well, if I drew an arrow like this, representing the displacement, what's the angle between the big arrow and the line arrow? This is F, this is D. What's the angle between these two? In other words, they're on top of each other. So it's like I have pointing this way, let's do it like this, pointing this way, and then I have another arrow pointing in the same direction. It's hard to do it, this thing is backwards. They're pointing in the same direction. What's the angle between two things pointing in the same direction? Hey, Tommy. Let's draw a little bit better like this. Let me see here. Here is 0. Good. Very good, Homie Betty. 0. Angle between them is 0 degrees. So if you put on your calculator 0 degrees, the cosine of 0 degrees is 1. So the answer is just FD. Cosine of 0 equals 1. So you do the maximum amount of work when the force applied to the object that's moving is in the direction of the object's motion. Hopefully that makes some sense. I'm going to have to erase all this. Oops, I'm going to do that. Let's do another scenario. Let's say I have a wall here, and I have a mass like this, M, and we have its weight acting down, we have friction acting up, and I have a force like this. What's the missing force here? What's the missing force in this scenario? The first correct answer gets a week stay at Castle Cyprus, Iranian Prize residence. Actually, better name would be Castle Pride. Castle Pride, located on the beautiful island of Cyprus. Free cooking by Mrs. Pride and luxurious views from the balcony. Well, weight is down. Weight is mg, right? Down. Friction force is up. The applied force is this way. If this was a scenario here, this thing would be accelerating to the right because there's an unbalanced force horizontally. It's the normal force. Remember the normal force? Normal force pushing back against the applied force. So this thing is not accelerating. As long as Mrs. Pride isn't throwing slippers. Yes. I heard that you're safe if you're out on the porch. Mrs. Pride will not throw slippers at you if you're on the porch or on the balcony. So how much work did any of these forces do? How much work does F do? And its V is 0. Now he throws it at you. See you, hero. Well, 0. Good, Grace. Work is FD cosine of theta. Well, if this thing is not moving, D is 0. So it makes the whole thing 0. So that's why you don't do any work if you push against a wall and it doesn't move. You're exerting an effort, you're exerting energy, effort, but you are not doing work. What about the resultant and the magnitude and direction? The resultant is the sum of vectors, which in this case it's all 0 because all these vectors cancel out. Now let's say that it's moving down at a velocity 2 meters per second, downwards. How much work is F doing now? Work done by F. And it moves a distance 5 meters downward. Okay, work is FD cosine of theta. So the force is to the right, right? So force is, let's say, in a positive x direction. So we'll say F sub x times D sub x plus F sub y times D sub y plus F sub z times D sub z. So we have Fx, this is Fx here. What's the displacement of the mass in the x direction? 0. So it's 0. There is no force in the y direction, 0. Even though that the displacement is 5. And this is 0 times 0. So there is no work. Or you could say F D cosine theta. Well, the force is F, D is 5. The cosine between them is what? So the force is this way, Displacement is this way. What's the angle between them? What's that angle there? $90, good. So what's the cosine of 90? Is 0. So it's still 0. So either way you do it, you still get 0. So you can think about this and say, well, the force applied is in one direction, but it's not, the object's not moving in that line of motion. So that's it. So that's that. So let's do another scenario. Involve this. How much work is done by the weight? How much work is done by mg? See if you can figure out how much work is done by mg. A gravitational force. Okay, so work is the weight, or is the force, mg, times d, times the cosine of the angle between them. So mg is the weight, we don't know what it is. D is 5. What is the cosine? What is the angle between mg and d? Hey DJ. I don't know, DJ. I've never heard that. See ya. What's the angle between the force down and the displacement down? Zero, right. So it's just 5 mg. Alright, what is the work done by the friction force? Alright, good, call me Betty. What's the work done by the friction force? Close. So, use the equation. Work is the force, F, times D, times the cosine of the angle between F and D. The friction force is F. Displacement is 5. What's the angle between F pointing up and D pointing down? Oh, I did this backwards. This is F, and this is D. Wow, Ben, that's amazing. $180, right. So if you put in your calculator cosine of 180, it's -1. So we get negative F, or 5F. Oops. Negative 5F. Hello, Jamie. So if we look at Newton's second law, free body diagram here, you have mg down and F is up, and the acceleration is 0. We know that the sum of forces in the vertical have to equal ma vertical. And if this is 0, the sum of the forces vertical have to equal 0. So the sum of forces vertical is F acting up minus D. Sorry, minus G. Sorry, minus mg, I mean. Minus mg equals 0. So F equals mg. So we plug it into here, you see we get negative 5 mg. So look, it's just the opposite of this. Kind of. Call me Betty. Kind of. You gotta be careful though with that. So what we can say now is the net work, I mean the sum of all the work done, is 5 mg minus 5 mg, which is 0. So the net work is 0. Right, as long as it's 180 degrees, yeah. So the net work is 0. So there's no net work done on this thing. Well, there is, but they all cancel out. And that brings up the next topic. You notice that A was 0. Whoops. But the velocity was a non-zero number. So let's look at that. So now we have to talk about something called kinetic energy. Kinetic means motion. So kinetic energy is the energy of motion. Energy of motion. Things moving have energy, kinetic energy. And the equation for that is 1/2 of its mass times its speed squared. Hey Genesis. Yes, you could do that. You could definitely do that. What happened to the music? Just got quiet for a second. So how much energy does this have? Does this moving mass have? It's 1/2 of its mass m times its velocity squared. So 1/2 of m times 4, which is 2m. So, and we measure, sorry, I should have mentioned this before, work and energy is measured in joules. Capital J, so we pronounce, that's how we write joules, capital J. I think there was a scientist named Joule, last name was Joule, that's where we get it from. So the work kinetic energy theorem, so the net work done on an object is equal to a change in its kinetic energy. This is a very important concept in physics. Work kinetic energy theorem. So we look at this scenario before, we said that the net work was 0, right? Well, that makes sense because its change in kinetic energy is 0. Kinetic energy is not 0, we said it's 2m. But the change in it is 0 because it's not accelerating. So that's pretty much, in a nutshell, what work and kinetic energy are about. So let's think of a problem to give you. Let me find one on the interweb. Okay, here's a good problem. Let me... Okay, see you. I'll take this away for a second. Put this problem on here. That's a good one. Okay. Here we have a scenario. We have a bullet. Has a mass of 2.60 grams, velocity muzzle of 335 meters per second, and can penetrate a 1-inch pine board with a thickness of 0.75 inches. What is the average stopping force exerted by the wood? For you. Call me Betty. So let's solve this. Well, we know that work is equal to the change in kinetic energy. So net work, I should say. So it's 1/2 mvf squared minus 1/2 mvo squared. So let's list what we've got here. The mass is 2.6 grams, which we have to convert to kilograms. So we have to move it over the decimal point 3 spaces to the left. One, two, three. Turn to kilograms. And its initial velocity is 335 meters per second. We had to write 8 1-inch pine boards, each with a thickness of 0.75. So the displacement here is going to be 8 times 0.75 inches, which we're going to have to convert to meters. So it's 6 inches. So I know that there are 2.54 centimeters in 1 inch. So 6 inches in 1 inch is 2.54 centimeters. And we know that there are 100 centimeters in 1 meter. So the inches cancel, the centimeters cancel. You get 6 times 2.54 divided by 100 is 0.154 meters. No, sorry, 1.2. So that's the displacement of the bullet. So what are we looking for? What is the average stopping force? We're looking for F average. Anyone have any idea what to do now? I'm going to highlight what we have in red, circle the things in red that we're going to need, possibly, or underline, I should say. Let's make sure anyone's still here. Yeah, we got 10 people. So what's the final velocity of the bullet? Velocity final of the bullet is 0. So work is F average times D equals 1/2 negative MVO squared. So we're looking for F average, right? So F average is negative MVO squared over 2D. Do we have all that information? We have M, we have VO, and we have D. So negative, yeah, Nook's running around, checking everything out. Whenever there's activity in the house, she's up running around. Initial velocity is 335 squared. It's going to be a big number. Over 2 times 0.1524. Here she is. Hi, Nook. Hi, Nook. You're looking for crumbs. Hi. Hi, Nook. Hi, Nook. Who's a good girl? Yes, she says hello, bed. So it's negative 957 newtons of force, average, to stop that bullet. Which makes sense. I mean, 900 newtons, let's see what that is in pounds. It's 215 pounds of force. It's about, I hate how I write sometimes. 215 pounds. Negative. Remember, the negative just means directions. So think about it. This makes sense. The velocity vector is this way. Right. This way. Nope, this way. That's right. I'm looking at this. This thing reverses the camera, so the velocity is that way. It's positive. The force is this way, which is negative, and that makes sense. That would have to be that way to slow the bullet down. So you can see the dominating factor in this equation is the velocity. The mass is tiny. The only reason the bullet has so much energy is because it's moving so fast. Take a bullet and you throw it at someone, it's not going to do much damage, right? It's the speed. The speed and kinetic energy is what does the damage. So how'd you like that problem? So you can find another one. Propulsion. Some of these are the same thing. Alright, I'll do this one here. Pegasus, what's up? Thank you for coming in. Hey, Greg. All right. Here, guys, pushing a lawnmower. So he's pushing down. So F, this capital, or this bold-faced F here is the force he's pushing. So the person does work on a lawnmower. Under what conditions would the lawnmower gain energy from pushing the mower? Under conditions would it lose energy? So gain energy. What kind of energy would it gain? What kind of energy would the lawnmower gain? You only know one type of energy at this point. Well, from what I've taught you anyway. Maybe know other stuff, but... Kinetic, right. So to gain kinetic energy, there has to be a network, positive network. So positive network has to be done. So what are the forces on this lawnmower? Here's the lawnmower. It's mass M. We have mg down, right? The ground is pushing back with the normal force. This guy is pushing like this, kind of at this angle. Is there any other force on this thing? Is there any other force on this? Genesis, you're on the right track. Friction, right, Greg. There's friction this way. So what we want to do is say network. What is the network on this thing? Well, it's moving this way, so we're going to say that F times the cosine of this angle. So the only force we can use is this of the man. So it's F cosine theta times D minus friction force has to be greater than 0. So sometimes that's confusing to people, so I just make it, if it's equal to 0, then there'll be no kinetic energy added or subtracted. So the net work has to equal, wait a minute. So FD cosine theta, I gotta put D here too, minus, or has to equal FD. So D's cancel, so the force applied, that guy has to apply, has to be equal to the friction force divided by the cosine of the angle. So if this is the scenario, this will be no kinetic energy added to lawnmower. If F is greater than F over cosine theta, kinetic energy added. There's a positive work. This will be positive work. Think of it like this. Positive work has been done. Here, work is 0. So we can say F is less than friction over cosine theta, and K is removed from lawnmower. Negative work would be done. That means the friction, right over here, this means friction does more work. Does more work than the man. So if friction is doing more work than the man does, that means it's going to be slowing down. So it's losing kinetic energy. So to keep the lawnmower moving at a constant velocity, a constant speed, the man has to push with whatever the friction force is divided by the cosine of the angle. So what angle would be best to push at? That's right, Ben. Well, we want the angle to be as close to 0 as possible. You're seeing people pushing their lawnmowers and they're struggling. What are they doing? They're leaning over. They're trying to get parallel to the ground. So that gives them, that means that most of their effort, their force applied, is going into moving the lawnmower. When you're pushing down on this arm of the lawnmower, this lever arm, whatever you want to call it, like this, you're losing this component of the force. This is just making the normal force greater. F sine of theta here is just increasing the friction because the normal force goes up. So that means the normal force goes up, which means the friction force goes up. So it's harder and harder to move it until you get to theta of 90. If theta equals 90, that lawnmower is not moving due to you at all. It's probably not moving at all unless it's self-propelled, because your force would be straight down and the lawnmower is trying to move this way. And it can't because there's no force in that direction. So you want your angle to be as close to 0 as possible within a comfort zone. Chainsaw, yeah, pulling the cord. Pulling that cord is doing work. Alright, that's enough for this. So anyone have any questions about this? Work kinetic energy theorem. Big deal. Work is a change in kinetic energy. That chainsaw's coming out soon, Ben. Hook that sucker up. As soon as I start feeling better. Yep. next week will be potential energy. So kinetic energy, remember, is the energy of motion. Potential energy is what we call stored energy. It's being saved for use at another time. I should say stored, not saved. Thank you, Katerina. All right, we got Physikē's premiere in 10 minutes. I'm gonna let you out early today. Yep, spring is stored energy, exactly. That's spring potential energy. So we're gonna deal with two types, gravitational and spring. When you tell us about Chernobyl, that'll be a whole different series of videos. I know all about Chernobyl, detailed. I never taught a class on it though, but I'd like to. Okay, everyone, thank you for coming in. Thank you, Ben, Genesis, Greg, Katerina, and anyone else still here? You be there for that? Okay, I'll start putting together I'd like to do that. I'd like to have a whole series of lessons surrounding Chernobyl. Oh yeah, that'd be great, man. All right, I'll see you all in Physikē's in a few minutes. See ya, Iranian. Greg, they don't like anything. You could have a lesson on how to make $100 and they wouldn't do it. All right, everyone. See you.
10.
Let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
This is Mission Control Houston.
Roll program. Roger, roll, Discovery.
Discovery's roll maneuver is complete. It is now in a heads-down position on track for its flight to the International Space Station. Discovery flying 365 miles per hour, 1.5 miles in altitude, 7 miles downrange from the Kennedy Space Center. Discovery's engines are throttling down as the orbiter passes through the area of maximum pressure on the vehicle.